Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Hannah Woodruff and Jason Aufdenberg with us today. Hello, Hannah. Hello, Jason.
Hello.
Hi.
Happy to be here.
Well, thank you so much for being to talk about your very lovely article. It's a very nice one. And Hannah, let's start with you. What's your geolocation? Where are you at?
I'm here in Daytona Beach, Florida,
Oh,
at Embry-Riddle Aeronautical University.
very cool. And how far along are you on your trajectory?
I just started the semester on my PhD in engineering physics and then graduated back in December with my master's in data science.
Very cool. Very cool. Well, let me be among the first to say, well, congratulations, Dr. Hannah. So very nice. And Jason, how about you? What's your geolocation?
So I'm also in Daytona Beach at Embry-Riddle Aeronautical University, and I've been here since 2006, and I'm
Nice.
a associate professor of physics and astronomy.
Very cool. Let's see, Daytona Beach. Well, we certainly have some water. What is the temperature these days in February 2025 as we record this? So are you still in your winter mode? You're coming in your summer mode?
It's been warm the past couple of days, but I know for a couple weeks it was really cold. We got hit with a cold front.
Okay.
Yeah, you might have seen the headlines with snow in Tallahassee.
Yeah.
We
Yeah.
didn't get snow here. It was perfectly lovely. It was 70 degrees and blue skies this morning on my bike ride. So
Very good, very good. So I'm in Phoenix, and we are definitely seems like we're starting to slide into our summer mode or our spring mode. So it seems like the cold temperature is gone. We'll warm up to about the 80s today, and so it should be very lovely. The only thing we're missing, of course, is a nice beach like what you have in Daytona. Very cool. And Hannah, what do you like to do for research?
So I have a bit of background for a few years. During my undergrad, I studied interstellar medium, specifically the H2 region around Spica.
Okay.
And then for my master's, delved into the stellar evolution and interior of the star itself, applying various data science, machine learning, and deep learning methods to that. While I was working on my master's, but now with my PhD, I would like to take those data science methods that I learned and implement them into the astrophysics community and return back to interstellar medium.
Very cool. Very nice. And Jason, what do you like to do for research?
I'm really into spectroscopy of really bright stars. So if
Okay.
you look at my publications, they tend to have stars with Greek letters in front of them. So I like to look at bright stars with new techniques. So I'm involved in interferometric observations and analysis of stars.
Cool.
And Spica stood out, as we'll talk about, because interferometry really spurred the theory. People want to understand more about the theory of stars. So there's kind of a back and forth between these really bright stars that have been known for a century. They get better and better data. We have lots of photons from really bright stars. So
Well, that helps.
yes.
Definitely helps. Very cool. Very nice. And that is going to bring us to this. Very awesome. This is a research note. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Exploring Spica's apsidal motion. Insights from feature engineering and machine learning with MESA and Hannah and Jason. Take us away.
Sure. So I would like to also include my other thesis advisor, Dr. Dumindu Samawarira. He taught me a lot of the data science methods that went into this research note. So I'll have Dr. Oftenberg explain some background of the star first.
Okay.
Yeah, so Spica, really bright star. It was a single star for all of antiquity up until the 19th century when it was seen to
Yeah.
have first it saw one set of spectral lines that were varying because the stars are going around each other, and then two sets of lines were found. So then you could get a mass ratio for the system.
Right. Yep.
And then the next thing that kind of happens is they realize in the 30s that the one of the um, elements of the orbit. So there are six orbital elements. One of them is the longitude of periastron,
Yes.
and that is advancing with time. which is telling us something about the distribution of mass and the tidal distortions of the star. So that's very interesting. And it turns out that period is very long, 121 years. So it takes over a century to make one extra sort of, so you can think of it as the stars go around each other in 4 days, but the whole orbital ellipse changes its orientation in space over 121 years.
Yes.
So we're interested in that because it gives us insight to the insides of the star, the mass distribution. And I guess I would also add that there's a larger theme here where people compare dynamical masses of massive stars with evolutionary masses. So
Yes.
when you measure the masses using spectroscopy and interferometry, you get sort of using Newton's laws, you get masses that way. And then when you use the luminosity and temperature on a track in a Hertzsprung-Russell diagram, that gives you an evolutionary mass.
Yes.
And Spica stood out as discrepant in these two areas. Yeah.
Okay.
So
Okay.
that is some of the big background. And so I'll tell you one more story. So the story is that in 1971, Spica's 6 orbital elements were known for the first time because it was spatially resolved. So there's only a few milli-arcseconds between the two stars, but in 1971, Urbis and Evans, which included Henbury-Brown and intensity interferometry, were able to
Okay.
resolve the star for the first time.
Cool.
And that's very cool. And so they got the inclination, for example, and all 6. So that allowed them to measure the absolute semi-major axis. And it turns out this apsidal constant, which is, you can think of it kind of like as the moment of inertia of an object, like the distribution of mass inside it.
Fair.
It's sensitive to the radius over the semi-major axis to the 5th power.
Yes.
So any uncertainties in the radius and the semi-major axis really are critical, and the uncertainty of the apsidal constant. So basically, I brought Hannah into this problem because as that radius and semi-major axis got more accurate, I wanted to know, since 1974, how have the models got better? Because this researcher Odell compared his apsidal constants with the observations, and they were fairly discrepant. We'll show you that in a figure in a moment.
Okay.
But what was the current status? Like, MESA is the sort of state-of-the-art, right, evolutionary code. What does it say that Spica's apsidal constant should be? So that's where Hannah comes in, and we run lots of models. Why don't you take it from there, Hannah?
Right. So we wanted to address the challenge of the theoretical models having some discrepancy with the simulations that were done and vice versa. So we implemented modules for experiments in stellar astrophysics, MESA. It's been used in other research for binary star systems, single star systems, etc. And so it's a newer sort of simulation project or program. So we wanted to implement that. And so we kind of varied it off of Claire's research in 2019 to calculate the apsidal constant over a wide range of stellar masses. We mainly focused on the range that Spica would fit in, obviously. Give or take some, we created a large set of parameters to put into the program via using its project enlist files and Perl scripts, etc. And so we ran those simulations and created a large data set for the primary star, because the secondary star doesn't have that much impact on it as far as we can tell right now. So we varied mass, metallicity, the convection mixing length parameter, the convective overshooting parameter, parameters such as that. And we were able to get a graph as seen in part A of figure 1 using almost 400,000 data points, where we can compare the MESA grid that was generated for this study versus what Claret got for a 12 solar mass star,
Okay.
which is similar to what Spica would be, compared to the observations of Tachenko in 2016 and other previous studies as well.
Okay.
Yeah, so I can tell you a little bit more about this figure in the upper left corner.
Okay.
So the Apsidal constant, the time in this diagram is not obvious, but at the top of these curves is near the pre-main sequence,
Okay.
and then it basically evolves downward with time. So it's evolving along the main sequence as you go down the curves.
Mm-hmm.
So Spica is sort of halfway through its main sequence evolution
Sure. Okay.
of where it is now.
Okay.
And the original Hanbury-Brown measurements are that, and Hanbury-Brown's intensity interferometer measurements lead to that big red area. So that was where we thought Spica was located in this plane of apsidal constant versus temperature.
Okay.
And the more recent observations push it up into that gray air bar.
Okay.
And so you can see for a long time, the best model was the purple model and the red data. So they did not overlap with each other. And that's what got us excited about what were things like now.
Correct. Yes.
And we're kind of happy for the state of science that the green model goes through the gray-black air bars. So it means the evolutionary mass and the dynamical information are consistent.
Very cool.
But that was for one mass and one set of parameters. What's the sort of uncertainty in the models? Like we can vary convection parameters and all, and the mass is not exactly 12.
Sure.
So that's where we ran a bunch of models and then subjected them to machine learning and neural networks. And so Hannah, take it away. What did we learn from
So
that?
all of those listed there. So random forest decision tree,
Mhm.
gradient boosting machine, linear regression, and support vector regression out of the machine learning methods. Then we have our deep learning methods, recursive neural network, feed forward neural network, deep belief network, convolutional neural network, generative adversary network, and then transformer. In parentheses next to those are the optimizers that just improve the performance
Mm-hmm.
in a wide range. 6 of them were tested for each one. Those are the top performing for each method. The
Gotcha.
results there, the mean squared error, root
Okay.
mean squared error, accuracy or R-squared percentage, and then mean absolute error. MSE, RMSE, and MAE, you want to be as small as possible, right? And then for the percentage of accuracy, you want it to be close to 100% as possible. So you see the results listed there, with random forests being, all of these being trained off of the MESA grid that was generated. We see that that lines up with
Got it.
Claret's and a lot of previous models.
Got it.
So we took that and trained that data set and trained these individual methods.
Yes.
And then the results are listed there. So we see that random forest was the best out of machine learning. And then for deep learning, it was a close tie between RNN and FNN, both using the Adagrad optimizer.
I mean, these are stunningly good numbers.
Yes.
I mean,
All of them trained very well.
yeah. I mean, that's
Yeah, so I think one of the bigger ideas that I learned about doing this study is how the data science can help us perhaps compute less models. If they're learning so well, we can generate points that weren't in the original grid.
Because it does.
Ask it, what would the MESA models predict for this other set of parameters? If we can really predict, if we can really train the model so well, yeah.
And it was a really big goal of this was, it is very time expensive and computationally expensive having to run. You saw there were 400,000 models. So if you're doing that over and over, and say you have a standard laptop, that's going to take forever. So why not just initially train these models to make it a lot more effective and efficient?
Yeah.
So we have all these greatly trained models, right? But how do we know that they're really so-called telling the truth and training as well as the numbers say? So we implemented various feature engineering methods to see how well based off of the training, how well the features were performing. So one of the top methods to go with is SHAP values, or Shapley additive predictions.
Okay.
And so the way these work in C and D is SHAP values are mathematically predicted based off of each model. And the values range from negative to positive. So those are correlations.
Okay.
So the more positive numbers means that it's more correlated to your final output that you're going for. So in this case, the Apsidal constant.
Right.
Then on the y-axis, we have each parameter listed from top to bottom. It ranks it. How important is it towards the Apsidal constant? So we see for figure C, the
Yeah.
effective temperature has the largest impact on the Apsidal constant, with on the right, more positive values being high. That means high temperature affects the Apsidal constant. Then for age, it's low age has the largest impact, low luminosity. And then if you see, it also scales all the way to the negative. So it means low temperature, high age, high luminosity actually takes away, negatively impacts the Apsidal constant. Same goes for
Gotcha.
D, which I meant to say figure, if you read the caption, figure or part C is based off of random forest,
Got it.
and D is based off of RNN.
RNA.
So that's the result for both of those.
Got
That's
it.
the neural network RNN, yeah.
Yes.
Yep.
So the top performing out of the machine learning, and then top performing out of the deep learning.
Here's D.
My takeaway from these SHAP models is that they really agree with the graph, right? If you look at the graph of the green line, when the temperature gets higher, the Apsidal constant gets higher, and that's what the SHAP correlations are telling us. This makes sense. There's a positive correlation with high temperature and high, and we all know from the HI diagram, when something gets, as the star evolves in age, it tends to get hotter. And so all these correlations are like, that makes sense, but it's good. It's good that the artificial intelligence is also the sort of finding the HR diagram in such a sense. It's finding these correlations that we all know from just looking at the evolutionary tracks. But it's good. But it has further insight into some of the more subtle parameters like metallicity and mixing link theory and stuff like that.
Surprisingly, not very sensitive to mass at all.
Right. Kind of have a narrow range of, because the mass is fairly well constrained, it didn't matter too much. Yeah.
Got it.
There is some spread. So the orange dots on the upper left plot, the orange dots are all the models that pass the luminosity and temperature cuts from the observations.
Got it.
So that's kind of like that's essentially giving the uncertainty in the Apsidal constant, given the uncertainties in the luminosity and temperature. So MESA would put all of those orange dots are consistent with the temperature and luminosity, and that then gives the spread of Apsidal constant from the multitude of different metallicities and overshooting parameters and masses in that box. So that's kind of our uncertainty in the theoretical Apsidal constant.
Nice. Very cool. Very cool. Okay.
So what are our conclusions, Hannah? I think you had some broader conclusions from the data science.
Yes, so a lot of the various methods and everything can be seen in Woodruff 2024, the various machine learning, deep learning, the feature engineering with 5 different methods being interpreted. A lot of dimension reduction also went into it, but all of that can be expanded on in that, or can be seen expanded upon in that. So what we found was that machine learning and deep learning does improve accuracy for the unseen input domains. It is a very necessary tool in astrophysics. Nothing to be afraid of with machine learning and deep learning, artificial intelligence, any of that. It greatly improved, I would say, the time it took to run models, at
Okay.
least in the future it will. And the best fitting was ultimately random forest RNN and FNN. It's really dependent on what you want to use
Mm-hmm.
or what your project is, but at least for binary star systems like Spica, those would be the models to really go with,
Cool.
is what we concluded. And that also luminosity, age, and effective temperature are really the parameters that affect the apsidal constant the most. Specifically, like I mentioned before, low age, low luminosity, and high temperature. They have the greatest impact on it.
Uh-huh. Yeah, and you mentioned here, and it was curious that of the two different methods, right, they sort of ranked these in different orders. Yes?
Yes.
Yes,
Yes. Right.
indeed. Yeah. So
We learned
they,
something a little different from each method, yeah?
right. So I think you can, I
Ah,
think Hannah can say a little bit more, right? There's some kind of a voting method, right, where you combine the methods together and weight them,
Right.
and they can kind of come up with a consensus view of the. So what's the name of that voting method? Am I
It was
remembering
just
that
a
correctly now?
voting mechanism that was created where we, towards the end of the study, implemented the top two machine learning and the top two deep learning. So it took the positives and the negatives with it of each individual method of those four total, combine them all with respective weights that were calculated for them, how much they would have an impact in this basically giant machine learning, deep learning system,
mm-hmm.
uh, and then predicted on a smaller subset of data. We looked a little bit at the feature engineering of that just to see if we could improve the machine learning and deep learning methods even more by combining them all, making it as strong as possible, in which it really did compare with the top uh, machine learning and the top deep learning. It was ranked up there.
Cool.
So yeah, see Hannah's master's thesis for all the gory details, which are
Yes.
cited. Yes.
Very cool. Very cool. And thank you, Vega, because I don't think we would have run that many MESA models without it.
Right.
Right. So that, yeah, so I guess the idea is you can run them fairly quickly on a supercomputer, but once you've trained with the machine learning, you could perhaps, if you want to refine models in a certain area or something, you could definitely explore predicting as well.
Yes.
So that's pretty interesting.
Very
I
cool.
can talk about the perspectives on the observational front moving forward. If
Okay.
um,
Let me, before we get to there,
sure.
ask one
Hmm.
question. So one of the original motivations that we talked about was, or the motivation for the study was how K2 had evolved over time since the 1970s.
Right.
So let's go there. So how does K2 change? How has
Right. So
K2
if you
changed?
go up to the figure,
Uh-huh.
it's getting so as a star evolves, the core gets more centrally concentrated, and so expect the apsidal constant to get more negative with
Okay.
time.
Okay.
But over the last 100 years is a drop in the bucket to the evolutionary age of Spica. So
Yes.
it's actually gotten less centrally condensed.
Okay.
It's from the 1970s to the 20 teens. The core is less condensed than we used to thought it was. So it's less evolved.
Okay.
Um, and that probably means its age is a bit younger than we thought it would be. There's all sorts of other angles. I mean, there's it's also in the instability strip, so
Oh,
it has oscillations that also probe the interior, and that's what the cool thing is about the apsidal constant. It's
okay.
just one way to look into the interior. The astroseismology folks can also tell us about the insides, and so one possible way looking forward is to try to join those up and see whether the astroseismology and the dynamical apsidal constant agree on what the inside should look like.
Okay. Very cool.
Yeah.
I'm with you. Very nice. Okay. Cool. Beautiful work. Beautiful work. Hannah, Jason, thank you for walking us through your very lovely article. And you're kind of hinting on it there, so let me go there and ask, where do you think we go from here, given the published article? Or is there additional observations to take? Maybe at different wavelengths, maybe with seismology, etc. Are there different machine learning or deep learning algorithms that one might want to try or combine to do? And so next steps, where do we go from here besides a PhD thesis or in addition to a PhD? So
You want to go first, Hannah?
Sure. Definitely there's a lot that could be done to add on to this. Look at transfer learning methods.
okay.
We could increase the size even more of the data set, as well as test it on other binary star systems that are similar to Spica.
Yes, yes.
So there's a lot that could be done on the data science side, especially with how new and quickly it is evolving.
Yes, it is.
We kind of ruled out using MESA has a binary star aspect to it, and we kind of ignored that because of the strong effect of the primary. The primary is probably 90% of the K2 constant,
Okay.
the Apsidal constant. So we ignored the secondary star, but one could imagine fully running MESA with 2 stars to actually check that, make sure that the binary influence of Spica B is really limited, as we think it is.
Mm-hmm.
And now, so no one has really done a good interferometric model for Spica since 1971. The Chara array on Mount Wilson, which has 6 1-meter telescopes, does have data in the can, and I'm in one of those projects to try to evaluate that. So the 2016 paper, they get the same major axis and they get the radius of the star, but we don't have a fresh set of 6 orbital elements, and that's coming eventually. Also, the Veritas intensity interferometer on Mount Hopkins also, I know, has been looking at Spica too. So there's fresh interferometric data that will emerge in the years to come.
Very nice.
So I'm looking forward to that. And that will require different models to interpret. So I'll play a role in that, trying to include all the gravity darkening, and they're not circular stars and all that good stuff. So that's where I come in the analysis. So there's models to get to the models, if you know what I mean. Anyway, there's layers to this thing.
Very cool. Very cool. Well, it'll be really exciting to see this develop over the next couple of years. Very exciting, especially in Spica itself and other binaries. So this is a nice technique. So very cool. Very nice. Thank you.
Thank you for having us.
Yeah, thank you.
That will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.